Dark matter is the invisible force shaping the universe. It determines how galaxies form. It controls how fast stars move. It decides whether galaxies hold together or fly apart. And without it, none of us would exist. Yet no telescope has ever seen it. No camera has ever captured it. And no experiment has ever directly detected it. Scientists call it dark matter. Not because it is dark in color. Not because it is dangerous or mysterious by design, but because it does not interact with light in any known way. It does not glow. It does not reflect. It does not emit radiation. To every instrument we have ever built, it is completely invisible. When you look up at the night sky, the universe appears bright and full. Stars burn with nuclear fire. Galaxies glow across unimaginable distances. Clouds of gas and dust stretch across space in brilliant color. It feels complete. Understandable, almost familiar. But this appearance is an illusion, because everything you can see, every star, every planet, every galaxy, every atom that makes up oceans, mountains, animals, and even your own body, accounts for less than 5% of the universe. Less than 5%. That means the vast majority of reality is made of something we cannot see, touch, or directly measure. Most of the universe is invisible. This invisible majority is not empty space. It is not nothing. It has mass. It has gravity. And it plays a crucial role in shaping everything we observe. Without it, galaxies would never form. Stars would never gather. Planets would never exist. The universe would remain a thin, diffuse fog of matter, incapable of creating structure. For most of human history, we had no reason to suspect anything was missing. Gravity seemed simple. Objects with mass attract other objects with mass. The more mass something has, the stronger its gravitational pull. Apples fall from trees. Moons orbit planets. Planets orbit stars. Everything followed predictable rules. As long as you could see the mass causing gravity, the universe made sense. But in the early 20th century, astronomers began to notice something deeply unsettling. The universe was not behaving the way it should. When scientists measured how galaxies rotate, they expected a familiar pattern. Stars near the center should orbit faster, where gravity is strongest. Stars farther out should move more slowly, where gravity weakens. This is exactly how our solar system behaves. But galaxies refused to follow this rule. Stars on the outer edges of galaxies were moving just as fast as stars near the center. According to everything we knew about physics, those stars should not be there. The galaxies should have torn themselves apart, but they didn't. Something was holding them together, and whatever it was, we couldn't see it. At first, astronomers assumed they had made a mistake. Early measurements of galaxy rotation were difficult. Telescopes were less powerful. Data was limited. Errors seemed likely, so scientists double-checked their work. Then they checked again. As technology improved, measurements became more precise. Larger telescopes allowed astronomers to observe stars farther from the centers of galaxies. Instruments became more sensitive. Datasets grew larger and more accurate. But the problem did not go away. It became worse. Again and again, astronomers measured the same impossible result. Stars at the edges of galaxies were orbiting far too fast. According to Newton's laws, gravity should weaken with distance. The farther a star is from the galactic center, the less gravitational pull it should feel. And yet, those distant stars were moving, as if they were still deep inside a massive gravitational field. The only way this could happen was if galaxies contained far more mass than what could be seen. This wasn't a subtle discrepancy. In many galaxies, visible matter accounted for only a small fraction of the mass required to explain their rotation. In some cases, more than 80% of a galaxy's mass was missing. Astronomers began searching for it. They looked for faint stars, stars too small or too dim to detect easily. Perhaps galaxies were filled with countless tiny stars, hiding in the darkness. But detailed surveys ruled this out. There simply weren't enough stars. Next, scientists considered gas. Galaxies contain vast clouds of hydrogen gas, much of it invisible to the naked eye. Maybe this hidden gas was providing the missing mass. Radio telescopes were built to detect it. Still, not enough. Dust was measured, cold objects were counted. Every possible form of ordinary matter was added to the equation. The numbers never came close. No matter how carefully scientists searched, most of the mass was still missing. This created a crisis. Either galaxies were filled with some completely unknown form of matter, or our understanding of gravity was fundamentally flawed. The problem didn't stop with galaxies. When astronomers studied clusters of galaxies, massive structures containing hundreds or even thousands of galaxies, the same issue appeared. Galaxies inside clusters were moving far too fast. According to visible matter alone, these clusters should have flown apart billions of years ago, but they remained intact. Something unseen was binding them together. The evidence kept piling up. Everywhere scientists looked, gravity was stronger than it should have been. At this point, the idea of missing matter could no longer be ignored. Scientists proposed that galaxies and clusters were embedded in enormous halos of invisible mass. These halos extended far beyond the visible edges of galaxies, providing the extra gravity needed to hold them together. This invisible substance didn't emit light. It didn't absorb light. It passed through normal matter almost entirely unaffected. It was dark and it had mass. The term dark matter began to gain traction, not as a placeholder, not as a guess, but as a necessary explanation. Something unseen was shaping the universe on the largest scales. And whatever it was everywhere. By the late 20th century, scientists were no longer debating whether dark matter existed. The evidence was overwhelming. Galaxies moved as if wrapped in invisible mass. Galaxy clusters held together by unseen gravity. The large-scale structure of the universe demanded something more than ordinary matter. The question was no longer if dark matter existed. The question was, what is it? The leading idea was bold. Dark matter was not made of atoms, not protons, not neutrons. Instead, it was thought to be made of entirely new particles. Particles that had mass, felt gravity, but barely interacted with anything else. If that were true, then dark matter particles should be everywhere, passing through planets, passing through stars, passing straight through your body right now. Trillions of them, every second, and yet we never notice. This made dark matter incredibly difficult to detect, but not impossible. Physicists proposed that, on rare occasions, a dark matter particle might collide with an atom inside a detector, producing a tiny, measurable signal. So they built detectors, not small ones, not simple ones, some of the most sensitive machines ever created. They buried them deep underground, beneath mountains, inside mines, under kilometers of rock, to shield them from cosmic radiation and background noise. They filled them with ultra-pure materials, liquid xenon, supercooled crystals, exotic sensors capable of detecting energy releases smaller than the vibration of an atom. They waited. Years passed. Nothing. So they built bigger detectors, more sensitive detectors. If you're enjoying this deep dive into the hidden side of the universe, consider subscribing. We explore science mysteries every week. And if this sparked your curiosity, leave a comment with what you think dark matter really is. Now, let's keep going. Detectors so quiet they could detect the heat from a single atom shifting position. Still, nothing. One of the most popular dark matter candidates was known as the WIMP, the weakly interacting massive particle. It was elegant. It fit existing theories. It explained the amount of dark matter observed in the universe. For decades, WIMPs were the leading candidate. Entire experiments were designed around them. Billions of dollars were spent, decades of work, And yet, experiment after experiment came back empty. No confirmed detections, no unmistakable signals, no clear evidence. As WIMPs began to fade from favor, scientists turned to other possibilities, like ixions and sterile neutrinos, ultralight particles that behave more like waves than matter. Each candidate required new experiments, new detectors, new methods. Again, scientists searched. Again, they waited. Again, the universe remained silent. This failure is not trivial. If dark matter particles exist, and if they behave even slightly like what we expect, we should have seen something by now. The absence of evidence has become evidence itself. It suggests that dark matter may interact with normal matter far less than we ever imagined. Or worse, that we may be looking for the wrong thing entirely. This is what makes the dark matter problem so unsettling. The universe is clearly telling us that something is there. Gravity proves it. Structure proves it. Cosmic evolution demands it. But when we try to touch it, to capture it, to measure it directly, it vanishes. Decades of searching have produced silence, and that silence is growing louder, because every new experiment rules out more possibilities. Every failure narrows the field. Every unanswered question raises a deeper one. What if dark matter is not a particle at all? What if it is something we don't yet have language for? Something outside our current theories? Something hiding in plain sight? By now, the search for dark matter has ruled out more possibilities than it has confirmed. Experiments have grown larger, quieter, and more precise than anyone once thought possible. Detectors buried deep underground have waited patiently for decades. Particle accelerators have smashed matter together at unimaginable energies. And still, nothing. This growing silence has forced physicists to confront a disturbing possibility. What if dark matter does not behave like a particle at all? Modern physics is built on the idea that everything in the universe is made of particles. If something has mass, we assume it can collide, scatter, or leave a detectable trace. But dark matter refuses to do any of those things. It interacts through gravity, and gravity alone. That makes it fundamentally different from every known form of matter. As experiments failed to detect traditional candidates like WIMPs, scientists began proposing more exotic ideas. Maybe dark matter is incredibly light, so light that it behaves more like a wave than a particle. These ultralight fields could flow through space, gently influencing gravity without ever triggering detectors. Or maybe dark matter exists in a hidden sector of physics, a shadow universe with its own forces and particles, completely disconnected from ours, except through gravity. In this scenario, dark matter would be real, massive and abundant, but permanently unreachable. Then, there is an even more unsettling possibility. What if dark matter does not exist at all? What if the universe isn't missing matter, but our understanding of gravity itself is incomplete? Some physicists have proposed that gravity behaves differently on very large scales, that the equations we use break down when distances become enormous and accelerations become tiny. In these theories, galaxies rotate faster, not because they contain extra matter, but because gravity itself becomes stronger under certain conditions. At first glance, this sounds appealing. No invisible matter, no unknown particles, just new physics. But there's a problem. Modified gravity theories struggle to explain everything at once. They can sometimes explain galaxy rotation, but fail at galaxy clusters. They can fit certain observations, but break others. They often require fine-tuning to match the cosmic web. Dark matter, for all its mystery, explains everything with a single assumption. Something unseen has mass, and that makes this dilemma especially painful. Dark matter works mathematically, it works observationally, it works cosmologically, it just refuses to show itself. Physicists are now caught between two uncomfortable options. Either the universe is filled with a form of matter we cannot directly detect, no matter how hard we try, or the laws of physics themselves are incomplete. Both options are deeply unsettling. If dark matter exists, then most of reality is fundamentally inaccessible. We are surrounded by something we can never touch or see, no matter how advanced our technology becomes. If dark matter does not exist, then one of the most successful theories in human history, our understanding of gravity, is wrong on cosmic scales. And the truth may be even stranger. Dark matter might exist, but not in any form we've imagined. It could be a field, a property of space itself, a relic of extra dimensions, or something so alien that our current theories simply cannot describe it. This is why the dark matter problem refuses to go away. Every answer leads to deeper questions. Every solution creates new contradictions. Every experiment narrows the field, but never closes it. The universe is telling us something. We just don't know what. And as detectors grow quieter and experiments grow more sensitive, the mystery becomes more profound, not less. Because if the most advanced instruments ever built still can't find dark matter, then maybe we're asking the wrong question. At first glance, dark matter may seem like an abstract problem, an invisible substance, a mathematical inconvenience, a mystery for scientists in distant laboratories. But in reality, dark matter is deeply personal, because without it, the universe would not exist as we know it. Shortly after the Big Bang, the universe was almost perfectly smooth. Matter was spread thinly across space, with only tiny fluctuations in density. On its own, ordinary matter could not clump together fast enough to form galaxies. It needed help. Dark matter provided that help. Because dark matter does not interact with light, it began clumping early, long before stars or galaxies formed. Its gravity pulled ordinary matter inward, creating the seeds of galaxies. Every galaxy you see today formed inside a vast halo of dark matter, including our own. The Milky Way is embedded in an enormous cloud of dark matter extending far beyond its visible stars. Without this invisible structure, our galaxy would have torn itself apart billions of years ago. The Sun would never have formed. The Earth would never have existed. Life would never have had a chance. Dark matter is not just a cosmic curiosity. It is the reason structure exists at all. And yet, for something so important, it remains completely unknown. We don't know what it's made of. We don't know how it formed. We don't know whether we'll ever detect it directly. Every experiment that fails narrows the possibilities, but also deepens the mystery. Because the universe is clearly telling us something is there. Gravity proves it. Cosmic structure proves it. The evolution of the universe demands it. And still, dark matter remains silent. This silence forces us to confront an uncomfortable truth. Human knowledge has limits. For centuries, science has advanced by turning the invisible into the visible. Atoms were once theoretical. So were bacteria. So were planets around other stars. Eventually, technology caught up. But dark matter may be different. It may not want to be found. It may exist beyond the reach of our instruments, interacting with our universe only through gravity. If that's true, then dark matter represents something profound, a part of reality we can infer but never touch. A reminder that the universe is not obligated to be understandable. Yet this mystery is also an opportunity. Solving the dark matter problem would revolutionize physics. It would reveal entirely new forms of matter, new forces, new dimensions of reality. It could unify theories that currently don't fit together. It could answer questions about the origin of the universe itself. That is why scientists keep searching, why detectors keep getting bigger, why theories keep getting stranger, why the question refuses to go away. Because somewhere in the universe, hidden in plain sight, is the answer to one of the deepest mysteries humanity has ever faced. And whether we find dark matter or discover that it never existed at all. The result will change our understanding of reality forever. The universe is not finished, surprising us. Most of it is still invisible. And some of its greatest secrets are still waiting to be uncovered. Which brings us to the final question, the one worth sitting with. If we finally understand dark matter, what do you think will change first? Let me know what you think in the comments. Thanks for joining me on this journey into the hidden side of the universe. Drop a like if this sparked your curiosity, and if this mystery intrigued you, you might enjoy what's coming next.